often the starting point for thinking about matter and what it's made of is an equation. You don't need to understand any of these equations. Suffice to say that it has in it every electron interacting with every other electron interacting with every ion in the material. So you can tell if you have trillions of electrons, you have everyone interacting with every other one. One can write down an equation, but it's almost as complicated as literally writing down every single electron in the universe. It's not something one can readily solve. And even if one said, maybe one has a supercomputer, and maybe at some point it will be able to crunch this equation and give you an answer, even if one were to say that, there's something else that happens that makes that very unlikely to give you the correct answer, and that's something known as emergence. So what is emergence? It's also something you might have heard in other areas, not just physics. It essentially relates to collective ensembles of objects collectively self-assembling to form something very, very different from the individual constituents. And you can think about people in crowds, so the collective behaves very differently from each individual member. You can think about something like consciousness. It would be very far-fetched to think of consciousness in terms of individual neurons, in cutting up the brain and saying, okay, what are the individual elements that make it up, and somehow I'm going to add them together and arrive at the functioning of the brain and consciousness. It's almost as absurd, it is as absurd to think about materials that are all around us that are made up of trillions of electrons and imagine that the collective self-organized processes that emerge from them, which are as complex and as exotic as consciousness, to be in some way derivable from a reduced equation of individual electrons. And this is just an example of one of the very exotic forms of emergent phenomena, which is superconductivity. So this is a superconducting material. The puck is a superconducting material. And this is a string of magnets. So essentially what you see happening here, you can see this is levitation. So superconducting materials have a couple of really interesting properties. Firstly, they conduct electricity perfectly without any loss. And this is a dramatic quantum property, and I'll show you an example in a bit. And the second is that they levitate. So if you put a magnet on top of a superconductor, it levitates. And this is quantum emergence in action. If you took a single electron or a few electrons, you would not get superconductivity. It would not be predicted from the model. The way superconductivity was discovered is that first people took materials, cooled them down to very, very low temperatures, discovered that they lost all resistance to the flow of electricity, that there was this amazing property of levitation. So it was an experimental discovery. And then they worked backward and said, okay, how can we form a model that now explains this?
Are you completely against the idea that we could, if we understood all of the constituent parts, say we had a complete knowledge of them, then we might be able to explain the emergent property in terms of its parts? Or do you think that they're always going to be missing something no matter how much we know about them?
I don't actually think that's a useful question, because at this point in time, right, we understand how two electrons interact with each other.
Right.
We don't even know how three electrons we struggle. In reality, in a milligram of material, there's 10 to the power 23 electrons. That's the number of stars in the observable universe. So I think it's a conceit, either for scientists or people talking about science, to talk about this idea of a theory of everything where we're at two particles. So we're not going to get to 10 to the power 23 particles, and the interaction between not just pairs of particles, 3 particles, 4, 10 to the power 23 particles. And even if we had such a theory, it would be reality, so there would be no point to such a theory.
Okay, good. Well, that was my best question. It's not a useful one either, apparently. So let's go downhill. Hilary, do you want to come back on something Suchitra said? Because you said, yes. That's true, I heard you a moment ago.
Well, I mean, I'd like to hear more about what you mean by encountering, but let me put that to one side. It seems to me that the idea that we have these, all of these bits, the electrons, and we've got a puzzle about how to describe the behavior of them as a whole, it is just the same sort of puzzle that I was describing initially. That it's the idea that maybe if we did have all of those bits, then we would explain the whole. And your thought that, well, we're not going to get there, so let's just engage in exploring how we encounter the emergent stuff, is still employing the notion that there are some bits at the level that we know about, electrons, and there is something more general. You haven't told us much about what the sort of overall behavior, what category you're going to use to describe that overall behavior. There is a problem of how you encounter it, is that you can't get from the smaller bits. So I'm not sure that there's really a difference, and that you're still relying on the notion that you've got the bits in the first place. So there is such a thing which is the electron, rather than an energy space, or however else we might describe it, and that you knew where you were, where your bedrock, you've got bits.
Actually, I'm not, right? Okay, I'll just be a little more specific as you asked for. Okay, so for instance, superconductivity is an emergent phenomenon, which you cannot describe in terms of individual electrons. Instead, you have trillions of electrons, the quantum behavior of which overlaps, and then you get this giant wave function, and that behaves completely differently to the individual electrons. So you do an experiment. By encounter, I mean you do an experiment, you discover something that behaves nothing like what we know of from individual bits. And then the theory that can be employed to describe it is a phenomenology, where we say we encounter this, and how can we describe it? And because we're only familiar with reductionist theories, we reduce it into a hypothetical particle. We don't start with the electron and make a theory to get to it, and we don't know that there will be such a theory. There might be an infinity of such theories, because yes, an electron would be a device if we went back to an electron. It's like, say there was the Escher progression, where you start with birds and you go to castles. If you see the castles at the end, that's superconductivity, you can't go back to the birds and say, how did you start with the birds and get to the castles? You could have started with oranges. You could have started with cattle. And the collective self-organization would have still given you the end product. So that's why I'm saying no, I'm not starting from that individual.
So I agree with that. But are you saying that the world is not differentiated then? Because I want to make the move and say the world's not differentiated. That's the consequence, the radical consequence of taking that through to all entities. Are you making that additional move?
I don't think the idea of there being an essential or a fundamental is a useful idea to even begin. So I wouldn't say it's differentiated. I would say, that's a nice project some people do, but does it tell us anything about the world? No.